introduce Professor Wolfgang Lenzen. Lenzen wasn't Wolfgang Lenzen. He's one of the most important Leibniz scholars in the world. So it's really an honor for me to have it here in the Institute. Giving a talk on one of my favorite topics, Leibniz logic. So thank you for coming. Enjoy.
Okay, so I'm allowed to talk to you without this mask.
You are.
Okay, first of all, let me also thank you for organizing this and giving me a chance for my first presentation of a logic talk in Mexico. I've traveled the world quite a lot, but I've never been to this country, and so happy that it worked out in the end. So the topic of my talk will be, as you can see, Leibniz's logic is kind of a link between traditional logic and modern logic. So, it used to work, but maybe it's off. Oh yes. Okay. So after a short introduction, talking about Leibniz as a philosopher and a logician, I will explain his main ideas about the relation, which will sound a little bit strange to modern logicians, is relation of conceptual containment. And then after that, I will touch on the conceptual conjunction, the conjunction of concepts, and the negation of concepts. And in this connection, also one has to consider the operator of the possibility of self-consistency of a concept, of a proposition. And in the last part of my talk, I'll give an outlook which goes beyond the first 5 chapters. So Leibniz was born in 1646 in the German city Leipzig. When he died in 1716, he left behind an enormous bulk of handwritten letters and manuscripts, which are all preserved at the Leibniz archive in Hanover. The catalogue of his handwritings, which was composed by Eduard Bodemann in 1889, this catalogue comprises no less than 41 different categories, ranging from theology, jurisprudence, medicine, philosophy, philology, geography, and various historical sciences to politics, economy, mathematics, physics, chemistry, and also technical sciences. All these manuscripts are planned to appear in print within the so-called Academy edition. Here you see one volume of this edition. Leibniz's sämtliche Schriften und Briefe, this is the official title of this edition. They are distributed over 7 series, and his philosophical writings, they constitute series number 6, which in turn consists of 6 volumes. The first volume was edited already in 1923, almost 100 years ago, and the edition is not yet completed. The most recent volume, his philosophical writings, appeared in 1999. It has a volume of about 3,000 pages. Leibniz's logical works have been first being edited by Louis Couturat in 1903 in this famous and oft-quoted book, Opuscule et Fragments inédits de Leibniz. This still valuable edition does not, however, contain the many earlier versions of text passages that were later crossed out and corrected by Leibniz. Such a text critical edition is only provided by the Akademie-Ausgabe, or alternative, we have to go back to the original manuscript, which may look like this. Unfortunately, this is anyway too small to read, but I promise you, even if you see it in the original format, you will have some difficulties to decipher this. This is the scan of a fragment entitled Principia Calculi Rationalis. You may perhaps see that it contains a lot of formulas involved in a way symbolically written like this. But the problem with these manuscripts is that they contain many crossed-out passages, which are sometimes very important to read what was wrong, why did he change it. And then also, especially on the margins, Leibniz's handwriting becomes smaller and smaller, and therefore, this is, for instance, something which you can hardly ever read, and even the editor Couture had problems in giving this version of the text, which I will not read here in full detail. You see the text is in Latin. Almost all logical texts of Leibniz were written in Latin. Some philosophical writings are also in French, and very few one in German. But basically, Latin was the language of the 17th century. Okay. If you don't read Latin, then you have to content yourself with a selection of Leibniz's logical papers that were edited in 1966 by Parkinson. It's this famous volume. It's a good volume, but only a few, really small selection of his important papers. Leibniz's most important fragment, the General Inquiries on the Analysis of Notions and Truths, has recently been edited in a bilingual Latin-English version by Massimo Mugnai. So let's have a look at the history of logic in general, and especially on Kant's opinion. In an often quoted passage from the Critique of Pure Reason, Kant expressed the view that until his time, that is, until the late 18th century, logic had not made any real progress since its foundation by Aristotle. Somewhat more exactly, Kant believed that logic, which he defined as a science in which the formal rules of thinking are extensively exhibited and strictly proved, represented the paradigm of a complete and finished discipline, which, once its basic laws had been discovered, could not make any step beyond nor any step behind the original version. Now, Kant certainly was not an expert in the history of logic, and he apparently had no deeper knowledge of the sophisticated logical investigations of the medieval or post-medieval period. However, most of these innovations fall into the field of propositional logic, while in the field of term logic, no comparable progress had taken place until the 18th century. Even in modern textbooks on the history of logic, it is widely acknowledged that the theory of the syllogism remained the dominating logical theory for more than 2 millennia. From a post-Freudian point of view, logic should roughly be divided into 2 levels: propositional logic and first-order predicate logic. The propositional calculus is usually built up from a set of propositional letters, with the help of the following truth-functional connectives: negation, for which I use the normal modern symbol, negation not P, then conjunction of two propositions again symbolized in that way, abbreviating P and Q, and disjunction with the symbol standing for P or Q, and implication P. If P, then Q, which of course will only partly be adequately captured by the modern symbol of so-called material implication. And finally, we have this fifth operator of material equivalence, which is a rough analog of P if and only if Q. From Aristotle onwards, logicians also considered diverse modal operators, such as elitic modalities, causal modalities, deontic modalities, and epistemic modalities. And all these give rise to various expansions of classical propositional calculus. Here today, only the following elitic modalities will also be taken into account. Necessarily P, abbreviated as usual by this box symbol, and possibly P, abbreviated, symbolized by the so-called diamond. And then I have this special arrow for the strict implication, and similarly the double arrow for strict equivalence between two propositions. On the level of predicate logic, the primitive propositions of the propositional calculus are more closely analyzed by means first of singular terms or names, symbolized by small letters from the beginning of the alphabet, and predicates symbolized by capital letters, mostly from the middle or from the end of the alphabet. And so these primitive propositions, first order calculus have the structure, logical structure f of A, saying that entity A has a property F, or G applies to B and C, meaning that the relation G exists between the object B and C, and so on. In general, the basic proposition predicate calculus has this form f of A1 through AN, where n is a natural number. With the help of individual variables, x, y, z, etc., one can introduce the usual quantifiers for every x and for at least one x. And on the background of this modern two-level model of logic, a very brief précis of the history of logic from Aristotle up to Frege, and even a little beyond, might be sketched as follows. When Aristotle developed his theory of the syllogism, he did not seriously deal with the laws and rules of the propositional calculus, but he rather presupposed the validity of certain propositional inferences. In particular, he relied on the basic assumptions of classical two-valued logic, which later came to be called the law of contradiction and the law of the excluded middle. Furthermore, Aristotle used the inference scheme of contraposition, according to which if one proposition logically entails another proposition Q, then inversely the falsity of Q entails the falsity of P. The first self-sustained investigation of the propositional connectives was done by some Megarian and Stoic logicians, such as Diodorus Chronos, Philo, and Chrysippus. But a much more extensive elaboration of the propositional calculus took place only in the 13th and 14th century, done by scholastic logicians who not only investigated the two's functional connectives, but also diverse modal operators, in particular William Ockham, Walter Burley, and Paulus Venetus, had a rather comprehensive knowledge of the laws of modal propositional logic. The next milestone in the development of the propositional calculus was set in the middle of the 19th century by George Boole, who not only developed a complete algebra of sets, but also a complete two-functional propositional logic. This development was rounded off towards the end of the 19th century by the outstanding work of Gottlob Frege, while modal propositional logic was established only in the early 20th century by C.I. Lewis. So this was the sort of tracing of the history of logic from Aristotle up to Frege, to C.I. Lewis. Now back to traditional logic. From the perspective of contemporary logic, the traditional theory of the syllogism covers just a small section of the logic of monadic predicates. The basic propositions of syllogistic logic are the four categorical forms: universal affirmative proposition, every S is P, often abbreviated by means of the vowel A, SAP, and I also give you the modern symbolization of this form. Then we have the universal negative proposition, no SSP, SEP, and its symbolic representation. Next, the particular affirmative proposition, some S is P, abbreviated in the traditional terminology by means of the vowel I, SIP, and finally, particular negative proposition, some S isn't P, abbreviated as SOP. Basic elements of the traditional theory of the syllogism are the laws of opposition and laws of subalternation. According to the laws of opposition, the particular propositions are equivalent to the negations of some corresponding universal ones, namely in the following way. The I proposition, some SSP, is equivalent to the negation of the universal negative, no SSP. And the second law says that some S isn't P is the same as the negation of every S is P. Furthermore, the traditional syllogistic is based on the laws of subalternation, according to which the universal propositions logically entail their particular counterparts, which says if SAP is true, if every S is P, then some S is P, and if second law, if no S is P, then some S isn't P. And all of these laws are usually summarized in the well-known square of opposition, which you can see here, which is familiar to each of you. Another group of simple inferences in the theory of the syllogism deals with the conversion to subject in the predicate term. According to the traditional doctrine, the universal negative, in particular affirmative propositions, admit of a straightforward or simple conversion, while the universal affirmative proposition can only be converted, as they call it, accidentally. That means if no S is P, then conversely no P is S. This is simple. Similarly, if some S is P, then some P is S, also a simple conversion. The third one says, if every S is P, then some P is S, because you cannot conclude that if every S is P, then every P is S would be invalid. At least this weakening is valid. The last conversion, the third one, follows from the law of subalternation in conjunction with the second real law of conversion. Some, though not all, traditional logicians admit negative terms, which they also call infinite terms. Technically speaking, this amounts to the introduction of a new operator, which, when applied to an arbitrary term t, yields the negative term not t. In what follows, this operator will be symbolized by means of the tilde. The law of double negation not only holds for propositions in this form, that the negation of p is equivalent to the original proposition, but also for terms in the form that the negation of the negative term t is the same as the original term t. Similarly, the law of contraposition may be transferred from the field of propositions into the field of terms, such that, for instance, the universal affirmative proposition, every man is an animal, is transferred into the proposition, every not animal is a not man. Or more generally, this would be the law of contraposition for terms. If every S is P, then every not P is not S. And finally, we have so-called obversion. The most important law states that a universal negative proposition like no man is just can be transformed into a universal affirmative proposition with a negated predicate. Every man is unjust. Or more generally, this is first law of obversion. No S is P is equivalent to every S is not P. Another law says that a particular negative proposition, like some man isn't white, can be reduced or can be considered as a particular affirmative proposition with a negative predicate, thus bringing out that as a whole, the Pn is no less affirmative than the Pa. Some man is not white. More generally, one obtains this law. Some S isn't P is the same as some S is not P. Thus the negation shifts from the copula to the predicate term. And finally, the well-known moods, which are perhaps best known in the description of the theory of the syllogism. Proper syllogistic inference leads from two premises to a conclusion, and all these three propositions have to be categorical forms. Syllogism itself must contain exactly three terms, say B, C, and D, such that following restriction is fulfilled. If B is the subject, or the so-called major term, and D the predicate or the minor term of the conclusion, then B must be conjoined with a third or middle term, C, in one premise, while the other premise has to connect C and D. The most famous examples of valid moods or syllogisms are, of course, so-called Barbara. If every C is D and every B is C, it follows that every B is D. Or Celarent, if no C is D, but every B is C, then no B is D. And Dari says if every C is D and some B is C, then some B is D. And the negative one here, if no C is D, but some B is C, it follows that some B isn't D. These are four most famous and so-called perfect syllogism of the first figure, but I will not enter in any details of this syllogistic moods. Next, I want to point out that at Leibniz's time, When Leibniz became interested in logic, the dominant textbook was the so-called Logique Royale, which has the official title La Logique ou l'art de penser, written by Antoine Arnaud and Pierre Nicole. One important doctrine of this work is the distinction between the extension and the intention or comprehension of a term. This is from their book, where they write, now in these universal ideas, there are two things which it is very important accurately to distinguish: comprehension and extension. I call the comprehension of an idea those attributes which it involves in itself and which cannot be taken away from it without destroying it, as the comprehension of the idea triangle includes extension, figure, 3 lines, 3 angles, and the equality of these angles to 2 right angles, etc. I call the extension of an idea those subjects to which that idea applies. The latter definition of the extension of an idea fairly agrees with our modern understanding, according to which the extension of a unitary predicate F is simply the set of all things to whom that predicate may truthfully be ascribed. However, there's a big difference between the traditional and our modern understanding of what constitutes the intention of an idea. Since the development of modal logic in the early 20th century, the intention of an expression is normally considered as something heavily depending on the respective possible word. According to the traditional view, however, the extension of F is not relativized to different words, but only mirrors the extension of the predicate in the actual word. This is also Leibniz's view. But there are some slight differences between Logique Royale and Leibniz. Arnaud and Nicole define the comprehension of F as a set of all essential attributes of F, that is, the set of all properties G, which are contained in F and which cannot be removed from F without destroying F. According to Leibniz's slightly different approach, however, the restriction to essential attributes may be dropped so that the intention of a term, predicate, is taken more generally as the set of all attributes which are contained in F. And this definition entails the following law. It's the law of the reciprocity of intension and extension. In symbolic terms, the extension of F is included in the extension of G, if and only if, conversely, the intention of F comprises the intention of G. Reciprocity of intention and extension. Leibniz defended this law in many writings. For instance, in the Elementa Calculi of 1679, he wrote, for example, the concept of gold and the concept of metal differ as part and whole. For in the concept of gold, there is contained the concept of metal and something else. For instance, the concept of the heaviest among metals. Consequently, the concept of gold is greater than the concept of metals. The scholastics speak differently, for they consider not concepts, but instances which are brought under universal concepts. So they say that metal is wider than gold, since it contains more species than gold, And if we wish to enumerate the individuals made of gold on the one hand, and those made of gold on the other, the latter will be more than the former, which will therefore be contained in the latter as a part in the whole. However, I have preferred to consider universal concepts, that is, ideas and their combinations, as they do not depend on the existence of individuals. So I say that gold is greater than metal, since more is required for the concept of gold than for that of metal. Our language and that of the scholastics then is not contradictory here, but it must be distinguished carefully. Now, this law, which I gave you in symbolic terms, entails straightforwardly the two concepts with the same extension also must have the same intention. It sounds a bit surprising, because according to the contemporary understanding of intention, this principle does not hold. One can construct predicates F and G, which have the same extension, but not the same intention. To quote a famous example of Quine, seems plausible to assume that, at least on our planet Earth, all animals with a heart have a kidney, and vice versa. Therefore, the predicates animal with heart and animal with kidney have the same extension, although only contingent. While their intentions, in the modern sense, their meanings, the meanings of these predicates differ widely. But this discrepancy between the modern and the traditional conception of intention fails to justify the verdict of Couturat, who claimed that the intentional treatment, as developed by Leibniz, is bound to remain confused and vague. It's not at all confused and vague. And it is also not, as Couturat believed, inferior to the intentional treatment as invented by Boole. As Leibniz never got tired of stressing, the logical relations between concepts can alternatively be treated in an extensional and in an intentional way. Thus, in the new essays on human understanding, the equivalence between the two points of view was defended as follows. The common manner of statement concerns individuals, whereas Aristotle's refers rather to ideas or universals. For when I say every man is an animal, I mean that all the men are included among all the animals. But at the same time, I mean that the idea of animal is included in the idea of man. Animal comprises more individuals than man does, but man comprises more ideas or more attributes. One has more instances, the other more degrees of reality. One has a greater extension, the other the greater intention. So once again, this is Leibniz's view of reciprocity between extension and intention. So I conclude this very long introductory part by pointing out that in the next sections I will show how Leibniz developed a logic which I call an algebra of concepts, which turns out to be the intentional counterpart of the normal extensional algebra of sets. And this gradually evolves from the traditional theory of the syllogism from Aristotelian logic in 4 steps. First important step is that Leibniz, in a way, abstracts or distills an abstract operator of conceptual containment out of the informal form every A is B, universal affirmative proposition. Second step is that he invents or just finds the operator of conceptual conjunction, which is inherent in the operator of juxtaposition of concepts, like in the example rational animal, just puts these two concepts together. This is juxtaposition, and it amounts to a conjunction of these concepts. Third important step is a thoroughgoing elaboration of the laws of conceptual negation, which goes hand in hand both with the invention of the operator of the possibility of self-consistency of concepts. By the end of the 1670s, Leibniz has come to realize that the traditional formulation of the universal affirmative proposition, the universal quantifier omne of every is basically superfluous. Instead of every A is B, one may simply say A is B, or equivalently, A contains B. Latin terms are est B or continet B. Thus, in this essay of 1679, he explains a universal affirmative proposition will be expressed here as follows: A is B, or every man is an animal. We shall therefore always understand the sign of universally to be prefixed in these formulas. The logical properties of this containment relation between arbitrary concepts are easily determined. Already in a fragment of 1676, Leibniz put forward what he calls the absolute identical proposition: A is A. Each concept contains itself, together with the what he calls hypothetical identical proposition, which amounts to this inference: if A is or contains B, and if B is or contains C, then A is or contains C. Hence, the containment relation is both reflexive and transitive. In what follows, I will formalize this containment relation by means of this symbol, which I ask you please not read as a set theoretical element relation, but it's my abbreviation for containment between concepts, which reminds me a little bit of the German word enthalten, which is a German translation of containing. So this is important to understand. A, this symbol B means A is B or A contains B. So then the just mentioned laws of reflexivity and transitivity take this simple form. Leibniz soon recognized that the identity, or as he also calls it, coincidence of concepts may simply be defined as mutual containment. Thus, in Elementa ad calculum condendum, he notes that if A is B and B is A, then one can be substituted for the other salva veritate, where a few lines later, he defines A and B are the same. He defines the same relation of sameness or identity or coincidence if one can everywhere be substituted for the other. This criterion of substitutivity is famous. Leibniz's law of identity. And of course, the identity between concepts will here be symbolized by the modern symbol. So we just obtain this law or definition: A equals B or coincides with B. It's just the conjunction of the two containments. The famous Leibniz's law of identity, the principle of the substitutivity of identicals, could be formalized by the following inference scheme: where alpha is an arbitrary proposition. Whenever A is equal to B, then, and if you have any proposition alpha which contains one or more occurrences of the term A, then this proposition is equivalent to the proposition where A is substituted by B. By means of these two basic principles, the following corollaries, according to which the identity relations reflexive, transitive, and symmetric can easily be derived, so corresponding laws in a symbolic way. As Leibniz saw clearly, not only can conceptual identity be defined in terms of conceptual conjunction, but also conversely, containment can be defined in terms of identity, but then you need something else, namely conceptual conjunction, to which we now turn. In Leibniz's own symbolism, the operator of conceptual conjunction remains rather hidden. When, for instance, the concepts animal and rational are conjoined to this expression rational and animal, or when more generally two concepts A and B are combined by mere juxtaposition into AB. This is just a formula. Anyway, as Leibniz points out in the early draft of the logical calculus, it follows from the very meaning of conjunctive juxtaposition that AB contains A, similarly AB contains B, because, quote, AB is way of formalizing something, wants to express just this, namely that which is A and which also is B. Hence, we have the following two laws. AB, this conjunction contains A, and AB contains B. Not trivial. In a later paper of 1679, Leibniz explains that the operation of a conceptual conjunction is also symmetric and idempotent, which means, here's a quote, it must also be noted that it makes no difference whether you say AB or BA, symmetry, or it makes no difference whether you say rational animal or animal rational. And now, next point, the repetition of some letter in the same term is superfluous, and it is enough for it to be retained once, e.g., AA, the same as A, or man is the same as man. Now, by symbolism, these laws take this form, which you see here. Leibniz further recognized that in addition to the previous laws of conjunction, which show that a compound predicate can be divided into several ones, also conversely, different predicates can be joined into one, which means if it is agreed that A is B, and for some other reason that A is C, then it can be said that A is BC. For instance, if man is an animal, if man is rational, then man will be a rational animal. And this is the general law. If A contains B and A contains C, then A contains this conjunctive concept BC. In Leibniz's Viper calculi, this law will usually be strengthened into an equivalence. For instance, he writes that A contains B and A contains C is the same as that A contains B and C. This will again be the symbolic version of this important law of conjunction. As I mentioned earlier, just as the identity operator can be defined by means of the containment relation. So conversely, containment operator might be defined with the help of conceptual conjunction and identity, namely according to this law, A contains B if and only if A is identical with A and B. This is a law which we find in many of Leibniz's papers. Here, for instance, in the general inquiries in paragraph 83, it is formulated in this way. Generally, A is B is the same as A equals AB. This principle admits a very elegant formalization of the four traditional categorical forms. The universal affirmative proposition is just this identity, A equals AB, or if you take S as a subject term equals the conjunction subject predicate. The universal negative proposition also can be formulated as an identity with the subject A and the conjunction of the subject A and the negative predicate non-B. And then the particular propositions will be obtained as negations of the corresponding identities, so as non-identities. A differs from A and non-B is a particular affirmative proposition, and a particular negative proposition says A differs from A and B. Now, the next operator, negation. Leibniz always used one and the same word, not, Latin non, to designate the negation either of a proposition or of a concept. His view about the negation of a proposition was quite straightforward. For instance, here he explains, if the affirmation is true, then the negation is false. If the negation is true, then the affirmation is false. If it is true, that it is false. Or if it is false, that it is true, then it is false. And if it is true, that it is true, and if it is false, that it is false, then it is true. All these principles or laws are usually subsumed under the name of the principle of contradiction. So this characterization is equivalent basically to the familiar truth table for the operator of negation, which entails in particular the law of double negation, which I already mentioned before. There's a law for terms, but here it is a law for propositions. Now, conceptual negation, negation of concepts. Now, this is a somewhat critical story in Leibniz's logic. During his research into the logic of conceptual negation, Leibniz encountered serious problems. From the tradition, he knew little more than the law of double negation, not A equals A, which is here written with the tilde symbol because it applies to terms, not to propositions. Also, it was difficult for Leibniz to transform the informal principle of contraposition into an appropriate law of what he calls his universal calculus. It is this law, term A or concept A contains concept B, if and only if the negative concept B contains the negative concept A. Furthermore, Leibniz happened to discover the following laws of consistency. The first one, number 4, says that A is always different from its own negation. And the fifth principle here says, similarly, if A is identical with B, then A cannot also be identical with non-B. These are laws of consistency, and he generalized these in the following way, that he said a concept, of course, a concept A will never contain the negative concept non-A. And the seventh principle similarly says if concept A contains concept B, then not also will it be the case that A contains not B. It's also a law of consistency. These two laws have been marked by me with a streak or star to indicate that something must be corrected here, but the basic idea is quite good. Now I come to what I call, officially also called, this cardinal mistake. This mistake of Leibniz's theory of negation consists in the frequent assumption that the one-way implication, which was formulated in the seventh principle, says concept A contains B, then it does not also contain not B, that this implication might be strengthened into an equivalence so that A is not B, isn't B, the negation of containment would be the same as A is or contains not B. So this formula makes clear what it is all about. This principle is clearly wrong. It is not the case in general that the negation of the containment relation between A and B, as you see on the left-hand side of the equivalent, would in turn be equivalent to containment between A and the negative concept. This is simply wrong. And this error, assuming that it might be true, is especially surprising because in general, Leibniz was well aware of the fact that the formula A contains B expresses the universal affirmative proposition. While on the background of the principle of aversion, the other formula, A contains not B, formalizes the universal negative proposition. So the negation of the universal affirmative proposition, of course, is not a universal negative proposition, but a particular negative proposition. So this is here, once again, in view of the traditional theory of propositions, the negated formula A does not contain B, and if A does not contain not B, represents a particular negative and a particular affirmative proposition, respectively. Hence, crucial principle negative negation 7 with the star basically expresses the law of subalternation, but this inference clearly must never be converted. The particular proposition can't infer the universal one. But Leibniz often mixed up these two formulas, A isn't B and A is not B. For instance, here in paragraph 92 of the General Inquiries, Leibniz emphasized that the inference from A does not contain not B to A contains B, or similarly from A does not contain B to A contains not B, is invalid. Okay, correct. On the other hand, a little bit earlier, namely in paragraph 82, he had mentioned that A isn't B is the same as A is not B. And this error is repeated again and again in this fragment or many other fragments. So he had serious problems with keeping this straight. The root of these notorious problems is the insufficient distinction between A doesn't contain B and A contains not B is closely connected with the distinction between singular and general terms. It's something new. If A is the name of some individual, or, and one could also say, if A is an individual concept, then the two propositions A does not contain B and A contains not B, though syntactically being different, these now are semantically equivalent because one may assume that for each individual X has a negative property, non-B, if and only if X fails to have a positive property, B. For individuals, this is okay. In this fragment of 1679, Leibniz explained two terms are contradictory if one is positive and the other the negation of this positive, as man and not man. About these terms, the following rule must be observed. If there are two propositions with exactly the same singular subject, first, of which the first has one, and second, the other of the contradictory terms as predicate, then necessarily one proposition is true and the other false. When I say exactly the same singular subject, for instance, if I say Apostle Peter was a Roman bishop and Apostle Peter was not a Roman bishop. Here we have no problems with singular subjects, with individual terms. The crucial law is cardinal mistake. It's not a mistake. This law is valid for the special case where the subject is an individual concept. But unfortunately, Leibniz failed to realize with sufficient clarity that this principle may not be generalized to the case where the subject A is an arbitrary concept. Thus, after the just quoted passage, he temporarily considered that out of the pair of propositions omnis homo est doctus, a few original Latin examples, and omnis homo est non doctus, exactly one would be true and the other false. But soon afterwards, he noticed this is an error, and he remarked that the generalized rule is wrong. However, a few lines later, he considered the rule once again in a more abstract way, omitting the informal quantifier expression omne, and then he repeated the mistake of postulating not only the basically correct principle negative 7. If the proposition A is B is true, then proposition A is not B is false, but also the incorrect conversion. If the proposition A is B is false, then proposition A is not B is true. Okay. Fortunately, the partial confusions and errors of Leibniz's theory of negation are highly compensated by a genius discovery, namely the invention of the operator of possibility or self-consistency of concepts. This operator shall here be symbolized simply by the capital P. P of A may be read as P, A, the term A is possible. Leibniz used many different locutions to express the self-consistency of the concept. Instead of A is possible, he often says A is a thing. In Latin, est res, or A is being, est ens, or also very simply, A is, est, this also means A is possible. Now, in Leibniz's logic, one can consider the conjunctive concept A and non-A. A not A as a conjunction, which of course is a contradictory concept. And therefore, one may define that the concept B is possible if and only if B does not contain contradictory concept like A and not A. This is a definition that Leibniz himself suggests. This is the formal way. of defining this operator of possibility. Concept is possible if and only if it does not contain this special contradictory concept, therefore not any other such contradictory concept. In order to get a clearer understanding of the truth condition of the proposition B is possible, let it be noted that the extension of the negative concept non-A must always be conceived of as a set-theoretical complement of the extension of A, because an object has a negative property non-A just in case that X fails to have the positive property A. Furthermore, the extension of a conjunction BC generally is the intersection of the extension of B and the extension of C, because again, an individual has a conjunctive property BC if and only if X has both properties. Therefore, it follows that the extension of A and not A is the intersection of the extension of A and in its own complement, and thus the empty set, which means concept B is possible if and only if its extension is not contained in the empty set, which means that the extension itself is not empty. At first sight, this requirement appears inadequate because there are many concepts, such as that of unicorn, which happen to be empty, but which may nevertheless be regarded as possible, that is, as not involving contradiction. However, as Leibniz explained, for instance, in a paper on some logical difficulties, the universe of discourse underlying the extensional interpretation of his logic should not be taken to consist of actually existing objects only, but instead to comprise all possible individuals. Therefore, the non-emptiness of the extension of B is both necessary and sufficient for guaranteeing the self-consistency of B. Clearly, if B is possible, then there must be at least one possible individual X that falls under that concept. This is Leibniz's idea. Then we briefly point out some important laws for these possibility operators. These laws, the first law says that if A contains B, but if A is possible, then also B must be possible. And a very important principle is this number 3, namely A, in general, A contains B if and only if it is not the conjunctive the conjunctive concept A and not B is not possible. This is a very important principle. The importance of this principle is evidenced by the fact that just in the general inquiries, Leibniz stated no less than 6 different versions of this law. For instance, in paragraph 151, he wrote, "We have therefore propositions tertii adjecti," various technicals of medieval logic already, reduced as follows to propositions secundi adjecti. Some A R B gives AB is a thing. So the universal affirmative proposition some A R B can be paraphrased as a thing being, that is a possibility of the conjunctive concept AB. Similarly, continuing this quote, some A R not B gives A not B is a thing or is possible. Every A is B gives A not B is not a thing, it's not possible. And no A is B gives AB is not a thing. So this idea gives the following alternative formalization of the categorical forms in terms now of the possibility operator, and also need, of course, conjunctions and negations. So, particular affirmative proposition says A and B is possible. Particular negative proposition says A and not B is possible. And then the universal propositions are corresponding negations. This is quite a different formalization of the traditional categorical forms. And this is an important point also for our conference, our workshop, which will start tomorrow, namely with the help of the P operator, the laws of consistency, which I mentioned earlier, can be corrected or amended as follows. The star now in exists is missing. It can be dropped, namely simply by giving this antecedent. Whenever A is possible, then A cannot contain its own negation. In the corresponding seventh principle, also under the premise that A is possible, it follows that if A contains B, A cannot also contain not B. As this principle shows, also the principle of subalternation that is influenced from the universal affirmative proposition A contains B to the particular affirmative proposition A does not contain not B, only presupposes that the subject term A is self-consistent, possible, and hence has a non-empty extension within the set of all possible individuals. Note also that the actions number 3 and 2 for the possibility that admit of a proof of the following counterpart of what in propositional logic is called ex contradictorio quantibet. Here in term logic, it is the principle that the conjunctive concept A and non-A, here I have inserted these brackets which could also be left out. The conjunctive concept, the contradictory concept, contains any other concept B. This is the counterpart of ex contradictorio quantibet. Just as a contradictory proposition A alpha strictly implies any other proposition beta, so the contradictory concept A and not A contains any other concept B. Okay, so I'll soon come to an end. It has often been noted that Leibniz's logic of concepts lacks the operator of conceptual disjunction. Although this is by and large correct, it does not imply any defect or any incompleteness of his algebra of logic, because the missing operator might simply be introduced by definition in standard way. Disjunction between the concept A and B, define it as the negation of the conjunction of the two negative concepts. It's just a note for propositional logic. And what is important on the background of Leibniz's own axioms for negation and conjunction, all the characteristic laws of disjunction can be proved, they can be derived from corresponding laws. So these usual laws, A contains A or B, similarly B contains A or B. If A contains C and B contains C, then also A or B contains C. All these laws can be proved within Leibniz's logic, which has the following result. Leibniz's so-called intentional logic of concepts, or say algebra of concepts, turns out to be probably equivalent or isomorphic to the usual extensional or Boolean algebra of sets. And in this sense, more than 150 years before Boole, Leibniz managed to transform theory of the syllogism into a complete and sound algebra of concepts. As a matter of fact, the full system of Leibniz's logic has even more to offer than only the algebra of concepts. For reasons of time, only two major ideas shall be sketched here. First, Leibniz discovered a really brilliant method to transform the algebra of concepts into an algebra of propositions. The core idea consists in stating a strict parallel between the containment relation among concepts and the implication relation among propositions. Just as A is B or A contains B is true when the predicate is contained in the subject, so a conditional proposition, if alpha then beta, is true when the consequent is contained in the antecedent. Thus, one obtains the following mapping of the formulas from the algebra of concepts into an algebra of propositions. A contains B is translated into alpha implies beta. Of course, it's a strict implication. Similarly, A is identical or coincides with B is translated into a strict equivalence between propositions. The negation of the concept is transformed into negation of its proposition. Conjunction is transformed into a conjunction of propositions, and the possibility operator is applied to terms is transformed or translated into the ordinary proposition operator, the cabal to propositions. And in particular, this important law, you remember, concept contains another concept B, the conjunction of A not B is not possible. This will be transformed or translated into the formula alpha implies beta, if and only if it is not possible with alpha and not beta, which C is just the ordinary modern definition of strict implication. Alpha strictly implies beta. If it's not possible that alpha is true, that beta is false. Second important thing in Leibniz's logic is his theory of so-called indefinite concepts, which mainly function as existential quantifiers. These quantifiers, of course, range over concepts, not over individuals. Thus, in the general inquiries, Leibniz explained, an affirmative proposition is A contains B. That is, if we substitute the value for A, one obtains A coincides with B, Y. This is indefinite concept Y. For by the sign Y, I mean something undetermined, so that BY is the same as some B, indeterminate B. So A is B is the same as A coincides with some B or A equals BY. This last formula, of course, has to be interpreted in the way of this principle number 4. A contains B if and only if there exists some concept Y, such as A equals BY. Occasionally, Leibniz's indefinite concepts also function as universal quantifiers. For instance, in the papers Semina Calculi Rationalis, Leibniz put forward a principle which says A is B is the same as if L is A, it follows that L is B. This law clearly has to be understood in the sense of this formula. A contains B if and only for every Y, Y contains A and Y contains B. Furthermore, in paragraph 32 of the general inquiries, Leibniz at least vaguely recognized that just as A contains B is equivalent to this formula with the eccentric quantifier, so the negative condition A does not contain B means that for every indefinite concept Y, A is different from UI. So this is a formula which at least vaguely was recognized by Leibniz as correct. Anyway, with the help of these indefinite concepts, this is a very important point, one can formalize Leibniz's conception of individual concepts. What is an individual concept? It is what we nowadays call maximally consistent concept. This can be defined in the following way. A is an individual concept if and only if, first of all, A itself is possible, it's consistent, and for every concept Y, the following holds: if Y is compossible with A, which means if the conjunction of A and Y is possible, then Y is already contained in A. So A maximally contains everything which is compatible with it. This is the basic idea of individual concepts as maximally consistent concepts. And this is not just my reconstruction, but it was clearly at least anticipated, or more or less formalized by Leibniz himself. Here, for instance, in paragraph 72 of the general inquiries, he writes, so if By is possible, and if the indefinite term Y is superfluous, that is, in the way that a certain Alexander the Great and Alexander the Great are the same, then B is an individual. If the term BA is possible, and if B is an individual, then A will be superfluous, or it follows if BA equals C, then B equals C. So perhaps we would need more time to discuss in how far Leibniz in this passage really has in mind what I have replaced here in symbolic terms as principal individual one. But anyway, I think this was quite a lot for an introduction to Leibniz's work, and so I'd like to thank you for your attention. Okay. But the last word, it's easy to see that an alternative formalization of the condition for individual concepts, the following one is an individual concept if and only if for each concept Y, this equivalence holds. A contains the negative concept Y if and only if A does not contain the concept Y. So as a corollary, it follows that the invalid principle, which Leibniz again and again considered as generally valid, in fact only holds for individual concepts. If A is an individual concept, then A does not contain B if and only if A contains not B. So this now, at least I think was all I want to say. This concludes my exposition. Thank you once again. Okay, the content of my talk today, if you want to read it in printed version, you could find it in this essay, the title Leibniz's Transformation of the Theory, which is Syllogism to Algebra of Concepts. It's contained in this volume. Otherwise, literature, more details you will find in this longer article, which I have composed for the Handbook of the History of Logic. which appeared in 2004. It's 83 pages, article, quite long. And if you prefer a shorter version, then I recommend you this online article, Leibniz Logic in the Internet Encyclopedia of Philosophy.
All right. So there is some time for studying, questions, comments. Any of you?
Thank you for your talk. That was very interesting. Very nice reminder of syllogistics. I was very curious about the parallel between set theory and concept algebra concepts, especially when it comes to principles like comprehension and extensionality. You mentioned that the Leibnizian view on extensionality pretty much coincides with our modern view of extensionality, but it is not the case with intentionality, right? And I was wondering at the time that modern set theory kind of introduces the intentional notion with the comprehension axiom or the subset axiom, if it is the switch, right? And I was trying to look at something like that here in the algebra of concepts, something of the nature like you may create a new concept by certain specific method, right? For instance, in set theory, we can construct a new set based on a certain property, right? Mm-hmm. So I was trying to look at that parallels between these two systems of logic, and I was wondering if you kind of have something to say about that point in comparison.
Well, first of all, I'm not sure whether I understood you correctly that you see an element of intentional logic in modern normal extended set theory.
I mean, it is like an extensional theory, of course.
Yes.
But the closest to an intentional thing involved there, I find that it's those properties we try to instantiate to create a new set. Obviously, it's not an intentional theory, so extensional. But I was trying to look at something similar to the comprehension scheme in the concept of.
Okay. Well, okay. I try to show that Leibniz is what I call algebra of concepts. Well, is in a way isomorphic to Boolean algebra of sets, and in a way, this parallel also means that for Leibniz, an intentional property which is given to us as an idea, in this sense, as an intentional entity, is extensionalized, can be viewed as its own extension or as giving rise to the set of all x such sets. This is correct. This is underlying Leibniz's thinking in logic. On the other hand, Leibniz did not develop, at least not in the fragments which I've talked about today, anything like a real theory of sets. But interestingly, but this would require another talk. He also developed explicitly some ideas how set theory, real set theory, may be obtained from a different corner, not from theory of syllogism via algebra of concepts, but from elementary arithmetic. He was a good mathematician, of course. He knew the elementary arithmetic. He wrote some very nice axiomatization of the elementary algebraic operations. And then he had the idea, why not transfer the simple laws of addition and subtraction to the realm of real things. in mathematics, you have addition, subtraction of abstracts of numbers. Instead, consider real things. What happens if you do not add 1 plus 1, but if you take one egg and try to add another egg, then you get 2 eggs, but one and the same egg added will not result to it. So this is a difference between what he calls real addition and subtraction versus this particular. And in the course of following these ideas, he discovered many interesting things, the theoretical operation of the intersection of two sets, and so on. This is another very interesting story. So he has also some ideas on set theory, but interestingly, he never has an analog to the what we consider as essential part of set theory, the element relation. This does not occur in this system.
Yeah, because I mean, you tell to us that some concepts contain other concepts, right?
Yes.
So I was thinking about separating those as we do with sets in axiomatic set theory. But I think this will help.
A question of clarification. How Leibniz interpreted the negative properties? Because A contains not B, but what is not B? Negative properties have the same ontological status as positive properties from Leibniz or for Leibniz?
In a way, yes.
In what way?
Well, he just admits the unrestricted operator of negating general term. Also, individual term. In principle, it would also be possible to talk about non-Socrates. Whether this makes sense is a different story. Leibniz doesn't discuss it, but it just has terms or concepts, and he freed it with the unrestricted application of the negation operator to each concept. You are skeptical about whether it makes sense. Or
No, I'm not. I was thinking, I was just had an idea in mind, because I would think that not B will be equal to A, so not A will be anything which is not A. Yes. But my question comes from, well, what would you think that this could be useful to maybe try to explain when we try to explain quantum logics or maybe computational computational field? What would be the best resources we may get from this Leibniz up to the Boolean algebra, which we know that is quite more involved in the computational field. So what would be the next step for today? So if you would like to go for example, rather than try to interpret the quantum fields, so something like that in the life at the same time. So what does logically that means? And that wouldn't that be something like let's call say a nonsense logic? What are we stating when we try to say, are we explaining the quantum theory, or what would be the next step from the Boolean algebra, and what the new process, or what will be where will this, or are we on time to take another step into the computational field, maybe another understanding point of view, or I'm very clear.
Okay, I mean, I understand that one may have reservations whether simple-minded negation applied to just anything makes sense. But I mean, also in the course of the history of logic, from Aristotle time to Leibniz's time, there have been many logicians who would not have accepted this liberal way of allowing to negate everything, so to speak. Infinite terms have been regarded with some suspicion by different logicians in the history. I'm not sure about Aristotle, actually, no, but Aristotle freely admitted negative or infinite terms. I'm not sure, but at least I've seen some medieval logicians who also were quite skeptical. But in Leibniz's logical writings, I didn't see any critical discussion of these issues.
So in this way, we can have an algebra of negative concepts. So if you have not B contains not B, we can formulate or expand this logic from that proposition. Not A contains not B, we can some other consequences. We can have this. We have this. An algebra of negative concepts, of negative properties.
Negative concepts, yes. I mean, as I said, Leibniz always used the same word, non. No matter whether it applies to an own proposition negation, or whether it applies to its term. He speaks of non-R. And so therefore also we have sometimes these problems when a containment relation is negated by a proposition negation, and changing, moving the negation to one or two terms, of course changes the meaning of the entire proposition. So he ran into some of these problems, not always, but sometimes. But it's just his way of using the negative particle non alternatively as a proposition operator or as a conceptual operator. Yeah.
I'm having a problem understanding what's A. We say A is A, and we say A contains A, but A's position accounts for can it be both?
No, it can't be both. Yes.
It's a concept you can build something about A with negative knowledge, but is that valid? Like, like chair is not a table, but it also is in Latin, and it also is in a lot of water, but does that tell you anything about the chair? And with propositions, I don't know if you can do something like that.
Okay, first of all, whenever you find a symbolic letter A or B in any of Leibniz's logical writings, it will stand for a concept or term, or you could also say a predicate. But especially in his later writings, he always has this parallel between relations among concepts on one hand and relations among propositions on the other hand in mind. And so it sometimes formulates principles about containing and so on, and says, if A is a proposition, then this means, but usually A always stands for a term or a concept. But he has this double interpretation in mind, at least in his later writings. And the other thing, you are stumbling about these logical principles. Of course, A is A. This is a trivial law of containment. You are wondering how can it ever be true that A contains B when A is not literally the same as B. An example, man contains rational. Concept man contains the other concept, rational. You have two different concepts. One contains the other. Does this answer your question?
The second one, yes, it actually is just that I see how you can deal negative knowledge with a concept, but with a proposition, not such.
Well, the clever idea was a proposition is that the entailment or implication relation between propositions as an abstract formal apparatus works just like the containment relation between concepts. This was one of his brilliant ideas that in this way you can derive the laws of propositional logic from his laws of concept logic.
And you say that Leibniz logic has something like exclusive limit, but in the presentation we have this scheme in implicative form. No, that is without making use their consequence relation. The question is, we have something like deduction theorem?
Deduction theorem, not in the real strict sense, because Leibniz was not aiming at providing a full axiomatic calculus with a distinction between actions and rules of deduction, and only if you have such a fully axiomatized calculus, you can talk about deduction theory and how it relates to provability of implications depending on the derivability formulas from action. So he does not have a modern axiomatic calculus, but he was aiming at least at summarizing the basic actions of his logic in many of his writings. And he uses implicitly certain rules of deduction.
So if I can jump in with this question. So he will accept that contradictory terms and joint contain anything, any other concept, but not that any proposition follows from a contradiction. Am I correct?
First of all, Leibniz himself never explicitly mentions this principle, which I say is the analog in this term logic, that a contradictory concept contains any other concept. It's not explicitly, but he has some other principles which make it easily provable. And for a similar reason, he only seldom talks about laws of propositional logic at all. Points out there's this parallel, so this mentions a few principles which follow from this idea. And among the principles which he mentions is not the classical ex contradictoria quadrivent, which had been formulated in the 11th, 12th, 13th century. Leibniz was very skeptical about that. Actually, I remember that he discussed a paper of Caramuel, which is another logician of the 16th century. Caramuel gave a very clear proof of the principle ex contradictoria quadrivent, and Leibniz has read it. And he was wondering, oh, that's strange. I doubt. I think it's a mistake.
I have a very simple question. What are the features of traditional logic that make it different from other logic? Was a simple question. Sorry.
Well, conditional logic, as I tried to explain, can be viewed as a very small portion of first order logic, plus monadic predicates. So it shows you. But what Leibniz made of this traditional logic resulted in much more, which comes closer to what we nowadays consider as normal logic.
What I have seen about the Leibniz concept of possibility concept of 5.1. 5.1, slide 5.1, the possibility concept. A is possible, so what is the concept for him? Or what does he consider a possibility? 5.1.
Let's see. We'll find it. 5.1.
Yeah.
But here it's about possibility operator. It should be
43.
one. Okay, thank you. No, this is the definition of the possibility operator. Term B is possible if and only if it does not contain a contradictory concept like A and not A. You mean that?
Yeah.
Okay. So, one question?
No, I just want to know because this has value of that. So contradiction A is not A. Yeah. Essentially, it's actually. Thank you. That's it.
Okay.
Any other comments? I have I have two questions. Sorry. I was a bit lost when you explained the invalidity of these connective like things in principles of application. For example, A doesn't contain A. What is the problem in that?
Okay, yes. Oh, this was quite in the beginning.
Slide 38.
Next slide. Oh yes, there they are, this principle. You're wondering why I would put a star on principle 6 and 7.
Yeah, I can understand the discussion about cardinal state and because it would be related with
Okay.
converse. This is the same one.
This is a different story. Okay.
Yeah.
This maybe okay, from a didactical point of view, this was a bit difficult to understand. So these four, what I call the laws of consistency, this is my formalization principles that Leibniz stated explicitly. I didn't give the quotation from the general inquiries, but he says A does not coincide with non-A, for instance, which would be principle 4, which is absolutely correct without any restriction. Then he says, which is a generalization or a stronger form, A does not contain not A, principle 6. He states it, and similarly, he states the counterpart, principle 7, if A contains B, then A does not contain not B. And later on, he tries to prove it, this. And in the course of his proof, which is very interesting, he notices, oh, what is, if A itself is an impossible concept, like B and non-B, then of course it will contain B and it will also contain non-B. So this principle does not hold unrestrictedly, as he first thought when he discovered it only holds for possible antecedents or for possible A terms.
The other question is rather technical. You showed by the end of the talk that Leibniz arrow is strict implication.
Yes.
But you have all the elements to define material implication. Like it's logic. If you have the algebra and the disjunction.
What might define it?
Yeah. So I can understand that the formal implication is this counterpart of payment, option, conceptual part. What would be the conceptual counterpart of material implication?
Yes, of course, it can be defined. Yes, but I can't. I'm sure I have written about this minor topic somewhere, but I forgot what it is because it's not a natural construction in the system of terminology. Some disjunction of A and then the negation of the second one, which makes no sense.
Okay, and we pray papers once more. Thank you. So
Yeah, another question. Can I see like, or can I see the extension and intention like this proposition as the sufficient and necessary conditions?
With
Can I see the extension and intention proposition, like these propositions, or no? I don't know if it was a proposition, but as a sufficient and necessary conditions. Are we meaning the same thing when we say that something is extensive and intensive and something is sufficient and necessary? The ones like because it comes about extension and another about intention, and Leibniz says something about extension. It was our presentation, can't remember the slide number, but
his general philosophical explanations, which he gives in not only in logical context, but in his familiar philosophical writings. It's just an explanation of how he understands the intention of a concept in contrast to the extension of explaining his view is the same as Aristotle's view, while he thinks that the scholastics at the contrary, but they are not conflicting. This law of reciprocity just shows you can view it in this way and you can view it in the other way. And he prefers the so-called Aristotelian view in contrast to what he calls the scholastic view. But I think this is, by the way, is a misnomer because most of the scholastic logicians that I have studied so far, they do not consider the extension of a term as something basic, and especially also as regards material implication versus strict implication. During the whole history of logic, from Aristotle to Leibniz, implication was almost always, or I would say always, considered as a strict implication. There's a discussion whether William of Ockham knew of material implication, but I think the people who think it can be found, they are mistaken. Strict implication is the ordinary view of implication all over this period of more than 2,000 years of.
Yeah, I think I ask you as well for your personal point of view about Husserl's logical system, phenomenological logic of Husserl from Husserl.
Keine Antwort. No.
I think that's it. Thank you everyone for the discussion, and thank you Wolfgang for the lecture, for the discussion as well.